Question number 4 asks us which two notations represent atoms of isotopes of the same element. So let's think about how isotope notation looks based on our periodic table. Based on our periodic table key, recall that we have the electron configuration, which sum to find the total number of electrons. We have the number of protons represented by the atomic number, and that's a bold number. And then we have the protons plus the neutrons, or the average number of protons plus neutrons, as the atomic mass. So notice that the proton number is in bold, and that's because the proton number identifies the element. So if you're looking for elements that are isotopes of one another, they should have the same number of protons, but different number of neutrons. So here we know that isotopes have to be the same element, so we can eliminate choice C and choice D. But now we're left with two choices. And when we look at the two choices, in choice number letter B, we can see that these two choices are exactly the same. So they're not two isotopes. Instead, they're the same element. So choice B is not. And here we can see choice A has the best choice because it has the same number of protons. They're both 50, but they have different number of neutrons because the mass numbers are different. Question number 6 asks, light emitted from a flame produced when electrons in the excited state. So we know that electrons have already jumped up to the excited state, and the light will be produced when the electrons return to the ground state. Now, to return to the ground state, they'll release their energy, and the ground state is lower than the excited state. So this is the best choice. So recall that when atoms have electrons on their in their principal energy levels, what happens is an electron in the ground state will absorb energy, so energy will come in. The electron will jump up to the excited state, and it'll move around here, but this is highly unstable, and then to regain stability, the electron will return to its original position, and it'll emit light. And that is the basic way in which a flame test or a flame spectrum is produced. Question number 7 asks for the historical order from earliest to most recent of the atomic models. So the two major choices are the first model, the hard shell model, or the electron shell model. So let's kind of draw out the choices that we have here. So the hard shell model would be that the atom is a hard shell like a billiard ball. That was Dalton's model. The electron shell model is that atoms have a nucleus and they have shells or rings of electrons surrounding it. And the wave mechanical model is the model of the atom where we have a nucleus and then the electrons are found in a cloud, a region outside of the nucleus that is defined by quantum mechanics or wave mechanics, basically defined by math. So we know that the first model was the hard sphere model. So that eliminates the choices C and D. And then after the hard sphere, we have the electron shell. And our current model is the electron cloud or wave mechanical model. It's really important that you understand that that electron cloud model can also be called the wave mechanical model. And in choice 8, we are asked to find atoms that include a metal, a metalloid, a nonmetal, and a noble gas. So what we want to do here is pull up a periodic table and see if we can locate these general families of elements and see if we can find which list of 4 includes one of each. Here on our periodic table, recall that metals are found to the left or under the staircase. So the metals here I will shade in red. So here are our metals. Non-metals, a metalloid is found on the staircase. And so here I'll shade in the metalloids. Now the metalloids must be bordered by the staircase by two sides, meaning we kind of have this L. So notice that boron is a metalloid, but carbon, which touches the staircase, is not a metalloid because it's not bordered by two sides. And then we have the nonmetals. Now, nonmetals are found to the right of the staircase. So these are all nonmetals. Don't forget that hydrogen is a nonmetal because it's found on the left side. Many students forget that. That's very important. And lastly, a noble gas. Now, noble gases are a special group. They're found in group number 18. So they are both nonmetals and noble gases. So here, when we're looking for metals, we can see that beryllium is a metal, as is potassium, iron, sodium, and zinc. So these are metals. Now, if we have to include one of each, anyone that has two metals is not a good choice, and the selection that has no metals, again, is not an acceptable choice. So that means that choice A is the best answer, and to prove why, we're going to make sure that we locate the metalloid. So the metalloid would be silicone. The non-metal would be chlorine. Chlorine's element number 17. So chlorine is the nonmetal. You can see it's right over here. And krypton, which is located right over here, element 36, is our noble gas. So that choice has all four choices. Beginning with question 9, we're looking for listing the elements with similar chemical properties. And recall that elements that have similar chemical properties are going to tend to be in the same column or group. So we begin with magnesium, aluminum, and silicone. Now, magnesium and aluminum are metals, and silicone is a metalloid. So they don't even kind of have the same general category. And again, they're in the same row, not column. So they will not have similar chemical properties. Choice B, we have magnesium, calcium, and beryllium. Now these are in the same column. They have the same oxidation number, the same valence electrons. All of these elements tend to want to lose 2 electrons to obtain stable noble gas electron configuration. So they will have very similar chemical properties. Now looking at the other choices, we also are given potassium, aluminum, and nickel. And while they're all metals, they are metals that are scattered throughout the periodic table, and they don't have any correlation with row or column. And we have potassium, calcium, and gallium. And so potassium, calcium, and gallium, they again are in the same row. So same row does not apply. It has to be same column, same valence, same oxidation state. Question number 10 asks, at standard pressure, which element has a freezing point below standard temperature? So first we're going to have to figure out what exactly is standard pressure and standard temperature. We can find that on the front page of our reference table, Table A. Here on Table A, you can see that standard temperature is 273 Kelvin or 0 degrees Celsius. Now that we're looking for freezing point, we need to refer to reference table S. Notice that the question asks about freezing point, but on table S, they only give melting point and boiling point. Recall that freezing and melting are essentially the same thing, or they happen at the same temperature. So here, since our reference table is in Kelvin, we're going to compare the freezing points to 273, and we're looking for a freezing point that is less than 273. So I've looked up the values and I found that we have 430, 2719, 2206, and 2032. So the number that is, 232. So the number that is less than 273 is the corresponding number with Mercury. In question number 11, we are looking for a brittle solid with low conductivity at standard temperature and pressure. So when I see low conductivity, that means we're looking for a nonmetal. So let's pull up our reference table and see which elements are nonmetals. So recall that metals are located to the left or underneath the staircase, while nonmetals are to the right or above the staircase. So sodium is a metal, as is aluminum, and sulfur and argon are both nonmetals. So we can eliminate the choices of sodium and aluminum. Now we have to go back to the other choice, that it's a brittle solid. Recall that in order to determine if something is a solid, liquid, or gas, we can use reference table S. We can set up a number line with the melting point and the boiling point and compare it to 273, which is the value of temperature for STP. Now remember that if 273 falls before the melting point, it is a solid. If 273 is in between the melting point and boiling point, it is a liquid. And after the boiling point, it is a gas. So again, the melting point and the boiling point will come from reference table S. And if you can insert 273 in a number line before the melting point and the boiling point, it will be a solid. If 273 falls in between the melting point and boiling point, it will be a liquid. And if it falls after the melting point and boiling point, it will be a gas. Now I could answer this question using this technique, or I could use a shortcut. The shortcut is, look at the elements that were given. We were given the element sulfur, and we were given the element argon. Argon is a special element in group number 18 called noble gases. Gases are not solid or brittle, so the best choice here is sulfur. Question 12 is a periodic trends table that asks to explain the trend for ionization energy. So the reason why the ionization energy decreases and related to the radius and the shielding effect. First, let's look at the radius, as that is found on reference table S. So when we use our reference table, we'll find group 1 here in the first column. We'll mark and look at what happens with the atomic radius as we go down the group. So here you can see the atomic radius changes from 12 to 130, 160, 200, and 215. So we can see this general trend is an increase. Let's go back to the question. So in the question, we can see that our radius is increasing, so we can eliminate the first two choices. Now we're left to figure out what is meant by the shielding effect. Now, the shielding effect is an effect brought on by shells. The more shells in which an atom has, the more shields it has between its nucleus in the center and its valence electron on the last shell. So we'll look at the electron configuration and see how the shells change. So hydrogen has 1 electron shell, lithium has 2, then we have 3, 4, and so forth. So we see that the shielding effect is increasing. For question 13, we're given an electron configuration. Now you have two choices. You could just scour the periodic table and look for a match. So that can be timely. So instead, recall that the sum of the electron configurations always equals the atomic number. For instance, when we look at the key on our periodic table, 2 and 6 for carbon 2 and 4 for carbon add up to 6. So if we sum up these electrons, we're going to have 25. So let's look on the periodic table for element number 25 and see if we can find an electron configuration match. Here I've blown up the reference table and you can see element number 25 is manganese 2, 8, 13, 2. So that is an exact match. Now we're asked to identify the family of manganese. Recall the important families on the periodic table. Alkali metals are found in group number 1. Alkaline earth metals are group number 2. Transition metals are group numbers 3 through 12. They are between the towers of the reference table. And noble gases are group number 18. So manganese, since it's here, it falls between the towers, it is a transition metal. Question number 14 asks us about elements that gain electrons. Elements that desire to gain electrons tend to be nonmetals. They want to gain electrons to obtain stable noble gas electron configurations. So here we're asked to characterize the ionization energy and electronegativity of nonmetals. So to do this, we're going to refer to reference table S. So here, what we'll have to do is compare the ionization energy and electronegativity of metals and nonmetals. I will circle the metals in red. So recall that we're looking for nonmetals. And elements that are nonmetals, those are the ones that are not circled. We're comparing their ionization energies to those that are. And we're also comparing their electronegativities to those that are circled. So we can see that comparatively, the ionization energies tend to be high, as do the electronegativities. Question 15 asks, which element has an atomic radius greater than its ionic radius? So let's take a second to look at the elements here on the periodic table. So generally, we can see that we have 3 nonmetals, so sulfur, fluorine, and oxygen are all nonmetals, while we have 1 metal, potassium. Now, when we go and we look here, and we think about ionic versus atomic radius, if the atomic radius is larger, that means the ion must have lost electrons. And recall that metals lose electrons. So in this case, the metal is the choice, and the nonmetals would actually have ions that are larger because nonmetals gain electrons to obtain stable noble gas electron configuration. Question number 16 gives 2 formulas of an element with iron, and it asks to which group on the periodic table does the element belong. So we know that iron has oxidation states of +2 and +3. And what we want to determine is what could the oxidation state of this element X be. So if recall that when elements form compounds, we write the symbols and then we cross the oxidation numbers. We can see that in one of the formulas with iron, that X has a 3, and that 3 comes from the iron. So this 3 would be crossed over to the X. And then the F would get a 2. So that means that this X likely has the oxidation state of 2. Now, to further make sure that 2 is a good number, let's look at the previous formula for iron with X, and it's FeX. Now, since iron has the oxidation state of +2, if X had the oxidation state of -2, recall that we'll cross the oxidation numbers and then we'll reduce. 2 to 2 reduces to 1 to 1. So now we have to find which group on the periodic table tends to have elements with an oxidation state of -2. Remember that when forming compounds, you have to have 1 positive and 1 negative because opposites attract. So looking here, we can see that elements in group 16 have an oxidation state of -2.